So we'd like to now go ahead and introduce our final speaker of the day, Dr. Tim Stark. Dr. Stark is a professor of civil and environmental engineering at the University of Illinois at Urbana-Champaign with an expertise in geotechnical engineering. Dr. Stark has been conducting research on geomembranes and other geosynthetics for over 20 years. He is the technical director of the Fabricated Geomembrane Institute at the UIUC. Let's welcome Dr. Stark talking about elevated temperatures and containment applications.
Thanks, Andy. Good afternoon, everyone. It's a pleasure having leading industry experts and practitioners here at the University of Illinois at Urbana-Champaign to offer this neat webinar. I hope we can offer another webinar like this in the future. I'd like to thank the GMA, Geosynthetics Manufacturers Association, for supporting this unique event. In particular, Jonathan Curry, the managing director of GMA, and his staff for helping us double stream this event today. My presentation today is focused on elevated temperatures and their effects on geosynthetics. This sort of follows up Professor Rowe's initial presentation on elevated temperatures, and I hope you'll view his webinar if you haven't already heard it, because he covers a lot of the introductory information about the effect of elevated temperature on geosynthetics. So my presentation has two big parts. First is a background on elevated temperatures in containment facilities, and then the second part is the effect of the elevated temperatures on engineered components or geosynthetics in particular. So the outline of the presentation here is, and the first topic is background and landfill zones and how big of a issue is this. So this is a map I assembled previously that identifies the range of elevated temperatures in the United States, and then recently I noted only 3 cases in Ohio, and the Ohio EPA produced this slide that shows 10 in the state of Ohio, so more than I had on my initial map. So it is a growing problem in elevated temperatures in containment facilities. So what are some of the typical causes of these elevated temperature events? Some of those are pictured here in various ways. The first is air intrusion. And here's a cover system, and even though it's been repaired, you can see a hole right there in the cover system, soil interim cover system, allowing air intrusion. Gas well operations. This is steam or smoke coming through a final geosynthetic cover system on a closed landfill near a gas well operation, and that was excavated and remediated. Incinerator ash, it arrives at the facility usually at an elevated temperature, and that gets kind of confined in the facility and can lead to an elevated temperature event. Industrial waste of different flavors. The pictured one is an aluminum production waste, and it could also involve shredded or scrap tires. Finally, C&D, construction and demolition debris type facilities, also can experience these elevated temperature events. I'll focus in on the next couple slides on air intrusion. These sources can be distant, in other words, not really close by. The picture I show you, it's fairly close by, but they can be fairly distant, and thus you're pulling in oxygen in from a greater distance. Here is some erosion of the interim soil cover, exposing the underlying municipal solid waste, and that is a source of air intrusion. If the facility installs a geomembrane to control odors or just control the facility a little closer, making sure the geosynthetics are tight and the geomembrane in particular, such as gaps between welds, extrusion welds, penetrations in the geomembrane, etc., is important, because there is a vacuum applied underneath this geomembrane, and if there are defects in that cover geomembrane, that can be a source of air intrusion. So here are the main zones in a landfill experiencing such an event. We have a normal operation zone out in front here, and then a gas and heating front coming towards the normal material, a smoldering front, and then a post-reaction / combusted pyrolysis zone behind that. And I'll get into the specific features of each of those zones in just a minute. So what is the progression of indicators? How do we know the facility is experiencing one of these events? Here is the sort of timeline from the start to the finish of one of these events. And there are 2, 4, 6 steps in this process, and I'll give you a summary of each of these 6 steps. Generally, the first step is a change in gas composition. And this can be readily detected if the facility is carefully tracking and creating trending graphs for various gases in the facility. So the top graph is wellhead temperature, and so this is the temperature measured at the exposed wellhead. And you can see it's trending along fairly consistently below the regulatory value of about 55 degrees C, and then it picks up, as you see here, going forward. So as that temperature changes, there are changes in the gas composition within the facility. So the bottom plot plots the ratio of the methane to carbon dioxide flow rate from a gas extraction well. And so you can see it's above 1. 1 or unity is a very good number for that ratio. And so it's tracking along above 1. And then notice right about the time, say about 550 days, when the temperature starts increasing, there's a pretty quick and dramatic drop in this ratio of methane to carbon dioxide. Right there. So having a trending graph of wellhead temperature, methane, and CO2 is very important. Those are just 2 parameters. Here's another parameter that's a good indicator of the gas front. Here's the graph I showed you on the prior slide of the ratio of methane to carbon dioxide. It's above 1 and then it drops quickly. This range from, say, 0.6 to 1 is sort of the transition zone, and that's why it's shaded. So below 0.6, there is some kind of reaction or event or change in significant change in gas composition that's occurring. The bottom graph is the carbon monoxide versus the same time scale at the same facility. You can see very low carbon monoxide up to about the same time as the decrease in the methane to carbon dioxide ratio. So carbon monoxide is a good indicator. It's generally not measured initially, so that would be an additional measurement once you see the change in methane and carbon dioxide. A good number for carbon monoxide is 1500. Yep. That's the red dashed line. Above 1500, that's a good indicator that there has been a significant change in the gas composition for the facility. So here's some data from a facility experiencing elevated temperatures, and this gives you a picture of how you can track the movement of the elevated temperatures by watching the ratio of methane to carbon dioxide. So here's the graph starting. Notice that the borings 1 and 2 are already exhibiting a very low ratio, much lower than the value of unity. So this is an area of concern or reaction that's occurring. But now watch, B1 and 2 are over here on the cross section. And now and the other borings or wells are at or above 1.0, say about 0.8 to maybe 1.4. So the reaction or the change in gas composition has not occurred in these other borings, wells B3 through B6. But notice as time progresses, right about here in 2011, there's a distinct drop. And this is in B3 and B4 and 5. B5. And it drops quickly below unity, so you can see that the reaction has gone from B1 and 2 here on the left side over to 3 and 5 over in this range. So not only does it give you an indicator that an event is occurring, but you can also plot this trend in a plan view across the facility and see the direction of movement. Okay, that leads us to elevated gas and waste temperatures and the heating front. So the wellhead temperatures now can be plotted on a plan view of the facility, and this graph in the upper left is April, December of the same year, so you can see the red, higher red color is higher temperature. April the following year, so this is 1 year after the graph above, and now you can see some very concentrated temperature zones on the order of 90 to 100 degrees Celsius in the wellhead. And now in December of that year, it actually looks like it became a little cooler, and that's one problem with using wellhead temperatures. They're subject to ambient air temperature, so as the weather cools, it looks like the landfill is cooling a little bit. One other thing to notice is there are some blue circles here indicating cooler temperatures, but notice that they're very concentrated. So what's happening there is the gas wells have a vacuum, cold air is being pulled in, and thus the wellhead temperature is decreasing. So in a plan view plotting wellhead temperatures, you can get a good view of what is happening within the facility. Here is gas temperatures and waste temperatures with depth. The red line is ambient or air temperature, and the other data on this graph is temperature at different depths. So the X's, the blue X's right here, are the shallowest depth in the waste, and notice they follow the air temperature pretty closely because they're only a depth of 0 to 3 meters. But as we go deeper, let's go to the deepest, 18 to 21 meters, that's the pink crosses here. Notice that they stay fairly high and are not really controlled by the ambient or air temperature. The other important difference between the depth of about 20 meters and the ambient temperature is, notice the difference in temperature is about 30 degrees Fahrenheit. And that's a good number if you're going to assess the facility and use wellhead temperatures. You need to add about 30 degrees Fahrenheit to get an estimate of what the downhole or waste temperatures are. Wellhead temperatures can be affected by ambient conditions, as I mentioned. As seasons change, the temperature change, and it can affect the measurements. Also, the temperatures at the wellhead can be adjusted or controlled on the surface. If you wanted to cool the well to protect the well and the infrastructure of the well, for example, you could put some ice bags on it and cool it down. So there are a lot of ways that the wellhead temperature may not reflect the downhole or waste temperatures. The next is increased gas. So we've had a change in gas composition, a change or an increase in temperature, and now an increase in gas pressure and flow. So pressures in typical cases, say with biodegradation, a pressure say less than 3 kPa. If there's an aluminum production waste, reaction can be on the order of or as high as 45 kPa. And if there is subsurface smoldering, it can be as high, generate a pressure as high as say 75 kPa. And the reason that pressure is generated is the ideal gas law. Going back to undergraduate chemistry, PV equals nRT. So there are a couple other parameters here, but the two big parameters that are important in the equation are capital T, where my pointer is, and that is temperature. On the other side of the equation is P, and that is pressure. So anytime the temperature goes up, the pressure goes up in direct function to it. And that's how high temperatures generate these high pressures. So here is a video just to illustrate how high these pressures can be. Oops. So this is the drilling of a gas well, actually a slope inclinometer in a facility, and the drilling process is going, and that is leachate being shot out the top of the boring on the order of maybe 20 feet high, because they're high temperatures generating pressure, shooting the leachate out the top. Okay, so next is leachate outbreaks and the increased volume of leachate when these elevated temperature events occur. So this is the diagram I started with, illustrating the gas front, heating front, and the normal phase of the landfill. And so as that front moves closer to an exposed slope of the facility, such as here, the condensate or the vapor condenses when it reaches the cooler area or the side of the landfill, and that creates a leachate outbreak right in this area here. And so what that could look like is shown on these figures. This photograph, there's a leachate outbreak on a side slope, and there's the leachate at the bottom. And this leachate outbreak can occur under high pressure, just like the one I showed you. This is an interim soil cover and a leachate outbreak right there, shooting the leachate out the side, somewhat like a geyser. So very high pressure. So with that high pressure and increased volume of liquid comes potential for slope instability. And a good thing to look for on these facilities are tension cracks. And these tension cracks will generally appear on the slope or near the crest of the slope, and they'll run across the slope, as you see with these little arrows right here. And it's important to monitor these cracks and make sure they're tension cracks instead of settlement cracks. Generally, the tension crack will reappear in the same location in a short period of time, maybe within a day or so. And if that does occur, that means the slope is moving fairly consistently. Okay. So this is another video showing the migration and movement of the slopes as the pressures develop due to these high temperatures. And generally what happens is the temperature goes up, the pressures increase, the facility sort of bulges out, and that's the time where it's most vulnerable to slope instability. If it can withstand that pressure and the settlement phase, which is next, starts, generally the slope will flatten and the stability will increase. So it's getting it through this high temperature, high pressure phase. So you can see that in this video. The elevated temperatures are going to start in cell 5, where my cursor is, and then migrate to the north into cell 7 and 6. And there'll be little vectors that come on the screen that give you an indication of the movement. The longer the vector, the more movement that has occurred. Okay, so there's July, September. So you can see movement of the vectors here in cell 5. Now they're moving up to cell 7, pushing out, 2012, 2013. And now notice the vectors in cell 7 are getting smaller because the material is settling in, sort of the souffle settling, and the slope actually decreasing. But the pressure pushing towards cell 7 and 6, and moving the slope out. That can all be included in slope stability analyses of the facility. Gas pressure can be estimated using a unit weight of gas of 12.8 newtons per cubic meter, a gas pressure head, and I gave you some typical range for biodegradation, aluminum production waste, and smoldering on a prior slide. But if you use 1 to 22 meters as the pressure head, then you can calculate the pressure that you can apply in your slope stability analyses and then check the factor of safety as a function of the induced pressure due to the elevated temperature. In this particular case, I calculated 22 meters times the unit weight, gas unit weight, 280. And here's a table that gives you a sensitivity of the factor of safety of the slope as a function of gas pressure. So initially there's no gas pressure, and the factor of safety is about 2.7, so stable. The MSW strength is still normal, but there's a high liquid level and a high gas pressure, and notice the factor of safety drops below unity. So a quick drop in factor of safety. Then if the waste is thermally degraded, which I'll talk about on the next slide, and that leads to a reduction in the shear strength parameters, you can see it drops the factor of safety even lower. So that can all be accounted for in stability analyses if you think the stability may be affected by elevated temperatures. Now on the last slide I showed that the shear strength of MSW decreases if it's thermally degraded. Here is a strength envelope for MSW, and it's a bilinear envelope. At low normal stress it has a friction angle of about 35 degrees and a cohesion of 6 kPa. At higher normal stresses, a friction angle of 30 degrees and a cohesion of 30 kPa. But if it's thermally degraded, it's been impacted by elevated temperatures, the cohesion drops and also the friction angle drops. And so thermally degraded waste would decrease to a friction angle of 20, which is this red line in the graph. And so you can see that that is a pretty substantial decrease in shear strength, which can be accounted for in your slope stability analyses. The pictures at the top here, this is a waste slide, a very steep scarp, stable because the material is acting like a reinforced mass, and thus the high strength parameters for MSW. But you can see if it becomes thermally degraded, all that structure of the waste and interconnection of the waste is lost, and thus the lower friction angle and no cohesion. Okay, that brings us finally to unusual settlement. Here is a facility that's experiencing elevated temperature. The red line across the top is the original height of the facility. So you can see the reaction. An elevated temperature event has caused a significant decrease in the height of the facility, and you can see it's moving towards the right, where over on the right it has not been impacted. As part of this settlement, you can get sinkholes, and this is a serious safety issue. The waste sort of gets hollowed out below the soil cover, and it can be a real safety hazard in walking on it. It can also lead to gas wells being extended or being left high in the air, such as these. And here is a video showing the settlement progression. So this zone in the middle will grow. The red is increasing red color is increasing settlement. And so this is sort of the settlement bowl dropping in. So if the slope can withstand the high pressures being developed, eventually the slopes will flatten due to the extensive settlement. And there's the settlement bowl. So now there's a settlement here in the middle on the order of about 20 meters. One more important thing about the unusual settlement is the timing of the unusual settlement. This is really important for assessing where the elevated temperature event is occurring. In that video I showed you previously, cell 4, if I back up, Cell 4 is off to the left, or your left here. It is not experiencing elevated temperature, and you can see a fairly consistent settlement with time of only about 1 to 2 feet per year. But in cell 5, experiencing the elevated temperature event, you can see a very accelerated settlement on the order of about 18 feet per year. Now, the importance is the timing of this. This increase, quick increase or acceleration in cell 5 occurs at about 800 days. But the gas composition change occurred that I talked about in the beginning at about 500 days. So almost a year later, the settlement, the unusual settlement shows up. So it's after the elevated temperature event has really impacted the area does the unusual settlement appear. And that's important for trying to identify where the reaction and elevated temperature event is currently in an effort to isolate it and contain it. You want to find that area it is in at the particular time and try to isolate it and contain it. If you go to the point where the maximum settlement is, it could already be past it. Okay, so the next big topic is classifying landfill zones. How do we delineate normal zone, the gas front, the heating front, and the smoldering/reaction front? So here's data from that same facility, and this is the area or the time where it has not been impacted. The gas well temperature is still fairly low. Remember, I showed you a regulatory value of 55 degrees C, so you can see the temperatures below 55 degrees C. Also, the ratio of methane to carbon dioxide is greater than unity. So everything looks normal. As time progresses, though, the ratio decreases, and notice the temperature after there's a significant decrease in that ratio starts increasing. So the ratio of methane to carbon dioxide is already down to 0.2 from a value of over 1, and now the temperature is starting to increase significantly. So how do we set that up to identify the gas front? So the gas front is delineated by a ratio of methane to carbon dioxide less than 0.6 and a temperature less than 60 degrees Celsius, which is about 140 degrees Fahrenheit. So that's the gas front. Now, how do we separate the heating front? So this is where the temperatures are increasing quickly, and using that same data set, the ratio stays the same, any ratio of methane to carbon dioxide below 0.6, and now a temperature greater than 60 degrees C or 100 degrees Fahrenheit. The heating front has reached that particular location. So how do we go from the heating front to the smoldering front? We use this graph here by Martin et al. It's called the 15-15 graph. It separates 15% methane on the horizontal axis right here and 1,500 parts per million carbon monoxide. And I showed you a line earlier on a plot with 1,500 parts per million carbon monoxide. So if the carbon monoxide is less than 1,500 and the methane is greater than 15%, notice out here about 35%, this is our normal operation zone. So less than 1,500, greater than 15%. However, if we transition from that through the heating front to the smoldering zone, notice that the carbon monoxide is greater than 1,500 and the methane is less than 15%, thus the 15-15 graph. Okay? So if I take the data from the facility that I showed in the prior slides, cells 5 and 7, notice cell 5 is actually in the smoldering zone. Cell 7 is over here in the normal zone. And as the heating front transitions from cell 5 to 7, as I showed with the vectors in that video, it transitions, the gas changes methane and carbon monoxide to the red zone, or greater than 1,500 carbon monoxide and less than 15% methane. So that's all summarized here on this slide. Gas front, temperature less than 140 degrees Fahrenheit. The ratio of methane to carbon dioxide less than 0.6. Heating front, the only difference is the temperature is greater than 140 degrees Fahrenheit. And then the smoldering front, less than 15% methane, greater than 1,500 parts per million, and a temperature greater than 175 degrees. So with those delineating zones, you can figure out where the elevated temperature event is at that particular time and develop a scheme for isolating and containing it. The last bullet point is also very important. Excessive settlement is a delayed indicator. That is not where the elevated temperature event is currently located. Okay, so what's the impact of these elevated temperatures on engineered components and the geosynthetics? Here are some engineered components in geosynthetics that have experienced elevated temperatures. If I start over here in the right, that's used to be a geonet, or a part of a drainage composite. This is a Hdpe drainage pipe that's collapsed. That's part of a geomembrane that experienced elevated temperature. And this is a temporary geomembrane cover, obviously inflated, a whale or a hippo, whatever term you want to use for that. Now that's experiencing elevated temperature on the bottom side of it. So the service life of Hdpe geomembranes in particular, and this relates to Carrie Rowe's first presentation, the 3 stages of service life, stage A, B, and C. You add those 3 stages up to give you the total service life. And that can be reported in terms of an index property such as tensile strength, losing 50% of a tensile strength, or Carrie Rowe in his presentation focused in on stress cracking and a significant increase in stress crack. So the service life, we add those 3 stages together, and I'll show you that on this graph on the right, and it's all based on the OIT, or initial oxidation induction time. So the stage A, B, and C are added together, so A, B, C, and the total is the squares here, and that's the service life. The important thing to notice is the dramatic drop in service life as the temperature increases with time. Okay, so the big question is, how much temperature do the geosynthetics feel in the facility, and for how long do they feel? If it's just a short period, maybe it's not a big effect on the geosynthetics, but if it's a sustained heat over a long period of time, it can impact the geosynthetics. So here's the time versus temperature plot for a facility, and these were detected by measuring temperatures in leachate collection pipes. So notice part of the facility remains at a fairly elevated temperature, 80 degrees C up here. But another part of the facility initially was not experiencing elevated temperatures. So for about 2 years it hovered around 45 degrees C, but then after about 2 years you can see a quick increase, and this increase occurring within a half a year to a year. So that's how quickly the temperatures can develop. And now the temperature is hovering about 60 degrees Celsius. This is important because if you conduct laboratory tests, as Carrie showed earlier today, you need to apply a temperature time history to the geosynthetics to see what the impact is on their long-term performance. So here is a temperature time history for one particular facility. So here's the initial landfilling. Some biodegradation occurs, so the temperatures increase a little bit to 115 degrees Fahrenheit. They remain constant, and they should remain constant, unless an elevated temperature event develops. So notice in this particular facility, an elevated temperature event did develop. It was a reaction, a metallic reaction. It quickly increases up to 175 degrees Fahrenheit, and it's maintained there for about 7 years. So if you wanted to simulate that in the laboratory in a liner simulator, you would subject the geosynthetics to about 7 years of 175 degrees, and then you can see it cools fairly quickly. And then you could assess the impact of the elevated temperatures on the geosynthetics performance. So if I use that time history and data produced by Rowe and Islam, if I use an immersion test where the geosynthetic is immersed in a solution, so both sides of the geosynthetic are subjected to the elevated temperature, here's stage A, B, and C, and if it has a low temperature, you would expect a long service life, say hundreds of years. Even in the simulated liner that Queen's University developed and are currently using, where the elevated temperature and leachate only touches one side of the liner system, notice the stage A, B, and C increase, and the sum, or the total service life, increases to about 900 years. So looks really good. And these are under normal service life temperatures, less than 55 degrees C. But if elevated temperatures do develop, such as I showed 175 degrees Celsius, now if immersion is used for the test procedure, you could be on the order of 5 years instead of hundreds of years. And if you use the simulated liner developed liner test at Queen's University, you're still less than 10, about 7 years. So a very dramatic reduction in service life of the geosynthetic with elevated temperature. So how do we protect the geosynthetics from the elevated temperatures? Some operational and design techniques to do that. Monocell, put the high temperature waste or waste that can potentially react in a monocell and have a thermal barrier or separation layer between that and the other parts of the facility. So if an elevated temperature event does develop, it's an isolated, contained area. And waste that could be isolated is aluminum production waste, magnesium type waste, and other waste that undergo reactions. An isolation break between the reactive waste and other materials if the facility is already in operation, or during construction, just leave an isolation break between the existing facility and the lateral expansion. Finally, a thick stone layer along the bottom that serves multiple features or functions. One is leachate collection, but also it provides a buffer and a cooling zone between the geosynthetics and the waste. However, if it's a stone layer, it's also a potential for air intrusion, which could also contribute to the elevated temperature event. So that's a catch-22. So how can we utilize geosynthetics in these elevated temperature events? One key use is to cover geomembrane, and I showed you some photographs of facilities that have used geomembranes to cover these elevated temperature events. They help control the odor, able to increase the vacuum underneath these geosynthetics and collect the gas and the temperature, high temperatures, and remove it from the facility. They decrease infiltration, which could contribute to the reaction in some cases, and the increased vacuum to remove liquids as well. But again, that's a catch-22, because if there's a high vacuum on the wells, there's a potential for additional air intrusion into the facility. Some of the geomembrane types that can be used for the cover geosynthetics or cover material: LLDPE, EVOH, woven coated polyethylene, flexible polypropylene reinforced, to give it some support. And here are some photographs of a odor control cover or temporary geomembrane on a facility experiencing elevated temperatures. So, in summary, the landfill zones, there are 5 main zones: normal operation, the gas front, the heating front, the smoldering front, and then the combustion/pyrolysis area or zone behind that. Gas wellhead temperatures can be a good indicator of what's happening in the facility, especially to plot the changes in temperature with time, but it should always be remembered that those gas wellhead temperatures are generally 30 degrees less than the downhole temperature. The gas front can be delineated by a temperature less than 140 degrees Fahrenheit and a methane to carbon dioxide ratio less than 0.6. The heating front, the temperature is greater than 140, same ratio of methane to carbon dioxide. And the smoldering front's delineated by the 15-15 graph. The methane less than 15%, the carbon monoxide greater than 1,500 parts per million, and the temperature greater than $1.75. Excessive settlement is the aftermath of an elevated temperature event. It's not an indicator of where the elevated temperature event is occurring. And finally, the service life of geosynthetics, and in particular Hdpe geomembranes, can be reduced significantly to even less than a decade in the presence of elevated temperatures. With that, I'd be happy to try to answer some questions. Andy?
Yep. All right, I got a couple questions here. First of all, what about possibly constructing a landfill below like an ordinary high water table, groundwater? Would that be considered a method to kind of keep it cool? That was an online question from Mick Leet.
Well, it would be cooler.
Yeah.
I'm not sure how you could permit it below water. I mean, if it's an inward gradient site, it could come in. But I don't know how if a state would permit a
Yeah, that'd be
below water and I guess dumping the waste below water. Or
But you don't remove it, you don't cure it, you don't solve the problem.
So you're talking about 140 degrees Fahrenheit at the surface. Some of the surface temperatures that you're seeing are greater than that.
That's an excellent point, Andy. That 140 degrees Fahrenheit and the 175 that I mentioned is a wellhead temperature, not a downhead temperature. So even though we're talking about 140 degrees Fahrenheit, it's 170 at depth. I forgot to emphasize that point.
So when you're talking about using temporary geomembrane covers at those elevated temperatures, are you seeing any potential for damage of any of the materials? I know you're probably not yet to melt point, but you could possibly have some issues. Do you see anything there?
Absolutely. The question is the elevated temperatures that are coming off the facility and reacting or influencing the bottom of that covered geomembrane are reducing the service life of that geomembrane. That's why they are called temporary covers.
Right. Right. Okay. Sam.
The pipe industry, the pressure pipe industry, comes with a hydrostatic design basis that's largely predicated on a reference temperature that's not 175 degrees Fahrenheit. Are you aware of their participation in response to these elevated landfill temperature issues? And if so, what is that? Are they working on high temperature pipe? What's going on there?
The question is the pipe industry addressing the elevated temperature event? Polyethylene pipe industry. I'm not sure about the pipe. There are, like gas well, there are elevated temperature or high temperature gas well pipes now being installed. The geomembrane industry, and I think this was what Andy was getting at, generally take the geomembrane to 150 degrees Fahrenheit. That is the sort of industry. If you go above 150, you're sort of outside the operating range. Having said that, in the recent 5 years, manufacturers are producing high temperature or temperature resistant geomembranes.
Right, right. No, good question, Sam. I've got a couple from here online. Praveen Joshi asks, would CCR facilities or tailings impoundments experience elevated temperatures?
Well, Gary may be a better person to answer the CCR part of it, but Gary's and AEP's facilities with FGD, generally that material sets up, it becomes very hard, and is not subject to reaction. And Gary, jump in if I'm off base there. The second part was
Tailings.
Tailings. Generally, the tailings, if they're sluiced, there's enough moisture there that it hasn't been a problem.
Right. Do you see waste rock or anything experiencing higher temperatures?
Waste rock can experience high temperature because you're percolating certain chemicals through to extract the metals.
That's right.
Absolutely.
That's right. Okay, good. One more from Joseph Stockbridge. What are your thoughts on the effect of routinely higher temperatures seen in a landfill that accepts sludges and readily decomposable organics, and the effect on the longevity of the liner and geonet materials?
So those particular materials can experience elevated temperatures. The sludges can come in at a high temperature, or they can be elevated through the biodegradation of the organics. So it's important to watch the threshold temperature, wellhead temperature of 140. That's a good indicator, and you're tracking the methane with time. And if you're crossing 140 degrees and the methane is decreasing towards 15%, if you're not already measuring carbon dioxide, you should measure it and then calculate that ratio, or measure carbon monoxide.
Okay, so Thomas Smallwood asks, what can a facility do to avoid this problem in the first place?
If you're going to take waste that is susceptible to elevated temperatures, and there's a calorimeter test developed by a PhD student here, Naveed Jafari, that you could perform to evaluate the potential for elevated temperatures to develop. So if you think it's going to develop elevated temperatures, that was some of the design ideas I had. A monocell, separate the waste within a particular facility. Just having a single facility accept only one waste isn't really good. So if you can set up a monocell within a facility that has a sufficient thermal barrier to keep it contained, is probably the best way to handle it.
Gotcha. Okay, I think that pretty much wraps up our questions from online. We have one question here in the audience, Gary.
So, Dr. Stark, is there any correlation or data that would show you've typically been looking at the methane, the gas temperature? Has there been any correlation that the leachate temperature has been increasing? Has that been tested?
The question is, have we also looked at leachate temperature as well as wellhead temperature? We have. I took those plot figures out to get me within 55 minutes, but yes, you can see similar increases in leachate temperature as well as leachate volume. And there are also changes in leachate composition that manifest themselves.
Great. I think that wraps up our questions, and I think that's pretty much it for the last presentation. So, thank you, Tim. And that concludes today's webinar. It's the end of a historic event, this first full day live streamed webinar through University of Illinois at Urbana-Champaign. Here you'll see on the screen some contact information. And this, again, I'll reiterate that the PowerPoint presentations, the whole recorded presentation, will be online and available through the GMA website and the FGI website. But if you want to contact Tim Stark, his information is there. My information, email is there. Also really want to thank Jonathan Curry, Managing Director of GMA, Dakota Hain from GMA, who coordinated this webinar today, Jessica Kivajarvi, who's the assistant at GMA, and of course Jen Miller, FGI coordinator here at University of Illinois. So thank you so much for all your help today. You can contact Jessica at GMA if you'd like a digital certificate of your PDH. Again, we thank you for participating, and feel free to reach out to us with any questions. And with that, we'll sign off, and everybody have a great weekend.